Thank you all for having me here. This is a real pleasure and an honor to be back at Princeton and to be offering what I think is probably the sole experimental talk of the Strings conference this week. So I appreciate the chance to tell you about the measurement that our team has made and announced recently. So up behind me is a picture of our telescope. It's an unusual telescope situated at the South Pole. This is the BICEP2 telescope, customized to measure the cosmic microwave background, the oldest light in the universe, coming to us from 380,000 years after the Big Bang, and specifically optimized, highly optimized as really a physics experiment designed to measure degree angular scale polarization of that CMB, and this is a map superimposed on the sky. That's the BICEP2 data set. So just about 3 months ago, 12 weeks ago, we announced our first results from that BICEP2 telescope. And the title of the paper is up here, The Detection of B-Mode Polarization at Degree Angular Scales with BICEP2. Just last week, the revised version of this paper was published in PRL. And the abstract, I'm not expecting you guys to read it from up in the back up here, but what I'd like to focus on with the first couple of slides is the team that put together this measurement, because it does take a substantial group of people to mount an effort like this, although we're a relatively small team compared to many large science projects. So this is most of us here at Caltech on the bridge. The BICEP and Keck array series of experiments, of which BICEP2 is the second stage, is collectively co-led by our groups at Harvard University, Xiaolin Kuo's group at Stanford University, Jamie Bach now leading the group at Caltech, and Clem Preich at Minnesota, with participation from a lot of other key institutions that have provided key technology and also people that have made this project work. And along the lines of people, let me highlight the ones who do most of the effort here. Usually, so these are the BICEP2 postdocs and graduate students, the young people who have dedicated their careers so far in science to making this measurement, to making the experiment work. Normally, I put this slide up and I tell people that these people will be looking for jobs soon, or they're out on the market, and they're all very talented and you should hire them. I don't know how many are interested in going into string theory. But keep your eyes out for all of these individuals. There really have been an extraordinary group of people. And to make an experiment like this, you need one particular individual who's willing to spend each winter at the South Pole when the last plane leaves. There's a 9-month period when it's completely inaccessible. The sun goes down, and that's when we collect the bulk of our data with these telescopes. So an individual has to volunteer to spend that year with the telescope completely inaccessible. And with BICEP2, extraordinarily, we had in 2010 Stefan Richter, and in 2011 Stefan Richter again, in 2012 Stefan Richter yet again. So he did an amazing job with this data set, and he's still doing well, believe it or not. Last, I really want to recognize someone who's not with us any longer. This is Andrew Lang, and it's important for us all to recognize him. In the BICEP and Keck array series of experiments, he really brought together and assembled our team, and it's not the only collaboration that Andrew has launched through the course of his long career. He viewed the search for inflationary B-modes as maybe cosmology's great wild goose chase, but he thought it was a goose chase worth pursuing, and so he's launched many collaborations and very generously sent them off and launched young careers in the process. When he invited me in 2006 to lead the BICEP2 experiment, it was a real act of generosity, but it was typical. Andrew's done that again and again through his career, and many people have similar stories. So this wild goose chase, what do B-modes have to tell us potentially about inflation? So I'm going to just very quickly, in pictures, because that's the way, like many experimentalists, we think, explain to you how the pattern we measure on the sky relates to the inflationary observable. So CMB polarization is radiation coming to us from the surface of last scattering. And if you imagine, say, a density wave whose k-vector is oriented along the surface of last scattering, perpendicular to the line of sight in the early universe, like this plane wave that's shown here. And there's an electron just before recombination that's scattering the photon field around it towards us, the present-day observer. you get a picture that looks something like this, and the photon field incident on this electron will have a local anisotropy that traces the gradients in the velocity field of the photon baryon fluid. And if I orient it in the way that I've shown here, that local anisotropy takes a quadrupolar form. It takes an m equals 0 quadrupolar form for a density wave like this. And so you get a quadrupole that looks like this, that changes sign as you move those scatterers from the crests to the troughs of a density wave. And as the electron is responding to the hotter radiation coming in from its sides and colder radiation coming in from the top and bottom, the net polarization that it would produce would be vertically polarized as the electric field from the hot radiation field here shakes it in a vertical plane, and that's the scattering that you see preferentially towards you. So you see associated with a plane wave in density like this, a pattern on the sky that looks like this. It's got polarization modulation that is always perpendicular to the k vector of the mode that's producing the physics behind this polarization pattern. So this is a so-called E-mode polarization pattern. And to describe any polarization pattern on the sky, you need an orthogonal set of modes, the so-called B modes that have polarization orientation plus or minus 45 degrees. So you can get that in the early universe, not with density waves. There's no way to orient the wave vector here to produce a pattern that has this symmetry. But if you introduce a new direction in the problem, the polarization of the gravitational wave here, shown by the hot and cold lobes of this m equals 2 quadrupole now, can be oriented such that the hot lobes here superimpose on the surface of last scattering if the wave vector comes out slightly to give you a pattern of polarization that modulates like this across that wave vector. Now, if I build up my microwave sky by a superposition of many such modes, suppose I add them coherently around a hot spot or around a single phase coherent spot here in the B mode case, you would get these typical radial and tangential patterns that are characteristic of E mode polarization. In the B mode polarization, the pattern swirls around that spot. You can get a clockwise or a counterclockwise swirl. And that's how you get these different characteristics patterns. You can see that the B mode pattern, the B mode part of the spin 2 polarization tensor changes sign under parity inversion, and the E mode pattern does not. So at the surface of last scattering, in the primordial CMB, it's only the tensors, only the gravitational waves that can generate the B mode polarization. Okay, so the E mode polarization was first detected a little over a decade ago. It's been detected by many experiments. This was the first one to do it, and this is another telescope at the South Pole. This is John Karlstrom's DAISY experiment. The same mount is now used by our Keck telescope. And the map that it produced looked like this. So you can perhaps see that this map looks like, looks vaguely like gradient flows around the hot spots and cold spots of the CMB. The polarization and the temperature are correlated at some level. But there's no perceptible curl part to this pattern. And I want to call your attention to the level of the polarization here. That's 5 microkelvin. So the typical polarization of the E mode part of the CMB is around 1 part in a million. So 1 million photons coming in like this, 1,000,001 coming in like that represent the polarization vectors in that map. The B mode part is much fainter still. So the long search for the inflationary B modes began, around the same time of those first polarization detections, until recently, we've had just upper limits searching for B mode polarization in the CMB at high galactic latitudes here. So the way that you characterize the expected inflationary signal is according to these power spectra. They peak at an angular scale, a multipole L of around 100, or a couple of degrees on the sky. That's the causal horizon scale at the surface of last scattering. And the amplitude is parameterized by tensor to scalar ratio R. So the best previous upper limits on R came from BICEP1. Those are these gray points here, R less than 0.7, coming from the B mode polarization, I should say. Now, up here at higher L, or smaller angular scales, the arc-minute scales on the sky, there's this other source of B mode polarization that comes from the distortion of the much brighter E mode pattern on the sky, the primordial E mode pattern, deflects by a few arc minutes on average, and so you get this smeared out power spectrum that traces the E mode spectrum, and that's recently been detected by these experiments here. Just in the past year, the South Pole Telescope and Polar Bear have put points up here directly detecting the peak of this lensing curve, and that's very exciting. There are going to be many other experiments that go after both of these signals in the coming near future, the coming year or so. Okay, so B modes from the ground as opposed to mounting a satellite experiment like Planck to go after this signal. What are the pros and cons of that? Well, you get from the ground the ability to concentrate your coverage on a small patch of sky. So you can go very deep to develop high signal to noise. You have the ability to pick that patch of sky to be as low in galactic foregrounds as possible, consistent with your knowledge of where those foregrounds are. But the flip side of that is that you have to observe through atmospheric windows. So you have limited frequency coverage from a typical ground-based experiment. And that means that foreground avoidance really is the primary strategy rather than deep foreground separation or removal. Working from the ground gives you the opportunity for systematic control with in situ calibrations. And because of the rapid technology cycle that's enabled by the fact that you can go and you can upgrade the telescope every year, as we do with this series of experiments, you can have a very large detector count deploying this year's technology. You can keep ahead of Moore's law, essentially, in the power of these experiments and how they grow. And you can observe a patch of sky relentlessly over and over again, and that allows a large number of consistency checks on the data set, large number of null tests. So it's a powerful recipe for a high confidence initial detection. So to show just now our specific example of a series of experiments that has followed this progression, you can see with BICEP2, starting off in 2006, through the currently operating Keck array, which is 5 copies of BICEP2, and the soon-to-deploy BICEP3, you can see a progression towards much larger detector counts, to the point where BICEP3 now has of order 2,500 detectors in a single telescope, starting just a few years ago with BICEP1, which had fewer than 100. So that's a progress that's mimicked by the other experimental groups that are working in this field right now and have similar advances in detector counts from the different technologies they're employing in their focal planes. So you can see we've moved from laboriously hand-assembled feed horns to photolithograph-based technologies that allow us to scale up the detector counts, essentially making CCDs that operate in the microwave using superconducting technology. So I'll have one more slide on that. So the BICEP2 experimental concept, to distinguish it from most other ground-based telescopes, relies on having a very small aperture telescope, one that's only large enough to resolve the degree scale expected signature of the inflationary gravitational waves. So it's got about a 26 centimeter aperture. The entire telescope is cooled to 4 Kelvin. The focal plane here is the new technology compared to BICEP1. And this 2-lens refracting system, while very simple, actually gives a very wide field of view. So in a compact system, we get extremely high throughput. As much raw sensitivity on the sky as a much larger telescope. We just sacrifice the resolution. So our detectors for BICEP2 and Keck array come from Jet Propulsion Labs. They're mass-produced superconducting detectors, not dissimilar from what the norm in our field has become. So I won't say much about these except that each one of these 4-inch silicon tiles has on it patterned an array of pixels, and each one of these squares, 64 squares per tile, has dual polarization detectors. So this pixel here consists of interleaved slot antennas, each of which are sensitive to either the vertical or the horizontal polarization of light coming in. And those are summed coherently on a transmission line to these superconducting transition edge sensor islands that are then read out with superconducting quantum interference device readouts. So we take all this technology down to the South Pole. It's a popular place now to mount CMB experiments. You can see the number of different CMB telescopes that are operating there. BICEP1, BICEP2, BICEP3 were in this building. The 10-meter South Pole telescope is our next-door neighbor. They're an independent group. The Keck array, which is currently operating now, is in this building. So it's a great place to do this research. You get a dry, stable atmosphere and 24-hour coverage of the fields that you can see from the south. There are many experiments that are successfully operating from Atacama, and Atacama, perhaps Greenland, are excellent alternative sites, and they offer differing trade-offs for the sky coverage that they present. So from the South Pole, our observing strategy, looking at a small patch of sky, really consists of this notion of relentlessly boring a hole on this 2% of the sky that we observe. You can see the telescope scanning back and forth. It's tremendously sped up in this video. Each one of those scans in real time takes about a minute forwards and back. And then the telescope is going, no, no, no. This is my 10-year-old son describing this video. No, 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 no. And then at the end of each hour, you'll see it do a little nod, an elevation nod, which gives it a calibrating signal. There you go. On the atmosphere, the common mode atmospheric signal gives us a real-time calibration check. So that's what the telescope would look like before the sun goes down. After the sun goes down, the nighttime sky at South Pole gets quite spectacular, and not many people get to see this sight, only people who went over with telescopes down there. So after taking data for 3 years, the BICEP2 data set looks like this. So the live time of the telescope in terms of calendar hours is shown in blue, and then after cuts that remove anomalous data when the telescope was misbehaving and the noise is high or there was bad weather, is shown in red. The instantaneous sensitivity of the telescope is getting steadily better through this period as we're learning to tune up the detectors better. But the telescope itself was kept at 4 Kelvin through this entire 3-year period. So by the end of this period, we had an instantaneous sensitivity of 15.8 microkelvin root second. So in 1 second, we achieve a sensitivity, net sensitivity with the instrument, able to measure 15.8 microkelvin. And the cumulative map depth that we build up over that period of time allows us to, in our map, make measurements that have noise that are at the 87 nanokelvin in degree pixels level on this field. So I'll show you that in a second. But another way of framing that is in terms of the total map depth that's achieved. If you express it as a single number, it's equal to 3 nanokelvin. So it's a very, very precise measurement that we've achieved by piling up all this sensitivity on a small patch of sky. So you can see during the course of 3 years of integration, the map depth now measured by looking at the noise levels in this jackknife map. This is one of those null test maps that we form by taking the data and subtracting the signal out of it and seeing whether the residuals are consistent with noise. And in fact, it continues to integrate down through this 3-year period. So you can see now the scale here is reaching 3 nanokelvin at the end of this period. And what's emerging out of the fog of noise that is receded here in these null test maps is this characteristic pattern in the Q and the U fields that looks crosshatched. That's because it's dominated by the E mode polarization. So that's the pattern that you would expect for the dominant E mode signal. So showing this in another way now, if you take our patch of sky, shown in context against Planck's beautiful all-sky CMB temperature map here, it's this 2% of the sky, or really 1% in the deepest region. This is the polarization map that we make if we combine the Q and the U together, and that's a superposition of the E mode and the B mode signal. We now need to separate those signals out. We can separate that map into Stokes Q and Stokes U, but that is a coordinate system dependent transformation. The right transformation to do, and this was taught to us by people like Matthias in the mid-90s. The transformation that lays the physics bare is to separate it into the E modes and the B modes, and we can do that very precisely in the case of these maps. We use a matrix purification method to separate out the ambiguous modes from the B mode map, and we're left with this. We're left with the B mode part, the swirling part of this map is much, much fainter than the E mode part, as expected. So now if I blow up the color scale on that B mode signal, we're measuring signals in this B mode map that are now characteristically one part in 20 or 30 million is the strength of these polarization vectors. So the way that we calibrate our experiment is against an extensive simulation pipeline. So we have here shown one such simulation. We go back to the time stream level and we inject signals that are consistent with the expected signal on the sky from lensed lambda CDM cosmology plus an instrument noise model, and we can generate hundreds of such simulations and test their statistics against our actual data map. And we perform the same filtering operations on the SIMS as we do on the map. And we use the SIMS actually to correct for those in the power spectrum estimation, and also to derive the uncertainties on the final power spectra. And the B-mode spectrum that results is this. So in blue is shown a temporal split jackknife, one of those null tests that's showing that, in fact, it is consistent with 0. All the jackknives that we form on the B spectra and the related EB spectra wind up being so consistent with just the expected statistics from noise. But the real data points are shown in black here. So the red line is the expected spectrum from lensed lambda CDM rising to the smaller angular scales. And it's consistent with the lensing expectation at higher L. There are a few high points, but not excessively high. They're high at the level of a couple of sigma. But at low L, there's a much more significant statistical excess over lensed lambda CDM, measured with high signal to noise. So it rules out the hypothesis that these black points are drawn from the solid red line distribution at a 5.3 sigma significance. So here are all of the spectra shown in a similar way, just for completeness, showing the jackknives and the different spectra that we form on our patch of sky, the temperature spectrum, the TE correlation, the EE spectrum, and the B-mode spectrum again. Okay, coming back to these jackknives for just 1 second. The ways in which we split the data to see if we consistently see the same B-mode pattern in each of the subsets we can form I won't get into the details other than to say that these splits are carefully chosen to try to highlight different systematics that might lurk in different subsets of data. So we have 14 such splits that we apply to the data. And for all of the B spectra, the jackknives actually look perfectly consistent with what we expect for the statistics of noise. Okay, so I'm going to pass briefly over calibration measurements, except to say this is a picture that illustrates how we can do these in situ, very careful instrument characterization measurements to do things like measure the polarization response of a single detector pair, or to map out the beam on the sky, which is very important for making sure that the signal that we're seeing is actually coming from polarization on the sky and not being produced by artifacts like a mismatch in the beams of the telescope. So the systematics analysis that we performed here, this is now showing, just for reference, a lens lambda CDM plus R of 0.02 curve here in the red dashed. And these are the systematics residuals that we've come up with for all the different systematic effects that we were able to imagine and simulate. So for any of those systematic effects that we could postulate, we find with high confidence that the apparent excess signal can't be explained by instrumental systematics. An extra check of this comes by cross-correlating our BICEP2 maps with BICEP1, the predecessor experiment, which on its own didn't have enough sensitivity to see this B-mode excess. But when you form the cross spectrum, you get noise at the geometric mean between the two data sets. And so you find when you cross-correlate it against BICEP1, the points here, now the gray points, are much noisier than the BICEP2 points in black, but they're consistent with this excess and, in fact, detect excess power in this region, the low L region, at about 3 sigma. So that's important because BICEP1 employs very different technology and might have different systematics than BICEP2. It's also important because the BICEP1 data set brings what very limited spectral information we have currently within our own data sets to bear, because it had channels at 100 gigahertz as well as 150 gigahertz. So the spectral index of the B-mode signal that we measure can be constrained by asking the question, does the amplitude of the signal that's traced out by cross-correlating BICEP2 and the BICEP1 at a different frequency match the amplitude of the BICEP2 spectrum? And if the B-mode excess were dominated by galactic dust rather than CMB, that has a blue spectrum, so you would expect little cross-correlation. You would expect suppressed power in this cross-spectrum. And if it were synchrotron dominated, so radio dominated, you would expect the 100 gigahertz power to be higher, so higher cross-correlation. So expressing that as an effective spectral index here, where the expectation for CMB is shown in blue, and synchrotron and dust are respectively represented here and there, we get this likelihood curve that is certainly consistent with CMB and weakly disfavors dust and synchrotron both. So if we show it for the whole data set, we have the green curve. If we show it just for the part of the data set that represents the excess above lambda CDM, we have the black curve. So for a dust only hypothesis, for example, you would expect about 1 in 10 times to get a likelihood ratio that favors CMB over dust, as often as the real data's likelihood ratio does. So certainly not a strong test, but evidence within our own data set that seems to favor CMB over a dust-dominated signal. I'll say I don't know if I've got this in my standard set of slides here, but a cross correlation with the WMAP data at lower frequency is a much more convincing test to constrain the level of the synchrotron contamination than this internal test with our own frequency data. Okay, so cross spectra between the 3 experiments are shown here now, BICEP2 and BICEP1, and BICEP2 and KEK as well. So the KEK array has been taking data relentlessly for the past 2 years and piling up a lot more sensitivity than BICEP2, and we're eager to get that data set out. The blue points here show that cross spectrum, and they show that excess as well. These higher L points, which seemed a bit high in the BICEP2 data set, do not seem similarly high in the cross spectrum with KEK. So we think there's probably a statistical fluctuation. And all in all, these cross spectra provide a powerful additional check of systematic origins for the apparent signal. So now if we ask, interpreting this excess as according to the inflationary gravitational wave model, what is the implied constraint on the tensor to scalar ratio R? Well, I'm not going to belabor the mechanics of this slide. The likelihood curve is shown here. It peaks at this value R of 0.2, and the error bar is really dominated by sample variance, by the number of modes that we've characterized in our sky. So this is a curve that treats the entire excess now as due to inflationary gravitational waves. And under that model, the null hypothesis R equals 0 is ruled out at 7 sigma. Now, of course, we know that inflationary gravitational waves aren't the only thing on the sky. And so although we think the synchrotron signal is very low at 150 gigahertz, of order 1% of our signal or less, according to the WMAP spectra and cross spectra, polarized dust is much more uncertain. So the BICEP2 region was chosen to have the lowest foreground emission based on available pre-Planck models, really looking at degree scale fluctuations in those models. So using models of polarized dust emission to estimate the foreground, and just running those models at their default parameter values, the ones that have been typically used in the community in past years, these are the projections in dashed lines for the level of power you would expect from those models, and the solid lines are cross-correlating those models against our data set. So both the autospectra and the cross-spectra are considerably lower than the excess signal that we measure. The autospectra, of course, could be low because these models are highly uncertain, and it's possible that they underestimate the amount of polarized dust power. The cross-spectra are low as well, and this could indicate limitations of the models in the way that they capture the polarized dust morphology on the sky. But this is the evidence that we were able to bring to bear on the data set here. Okay, so the constraint on R under foreground projections, if we just subtract these curves, the contributions from dust implied by each of these curves off from the data points, it causes R to shift down, of course. And it shifts down by an amount that depends on the level of those curves. So the statement that we made, the probability that each of these models reflect reality is hard to assess, is an important one to bear in mind. And this is something that we tried to clarify in the version of the paper that we put out last week. And it's important to recognize the uncertainties could go in either direction on these models, but they are large enough that if you push them in the upper direction, they could equal the entire signal. But under these default model parameters, R equals 0.15 to 0.19 is what you get for the most likely value of R. So you need to jack up the power in these foreground estimates by a factor of 5 to 10 for it to equal the entire signal. Okay, so I think I'm going to pass over this slide, unless we get questions on it. The conclusions circa March 17th are that we've made a measurement of the deepest polarization maps on these angular scales to date. So these are the noise levels in those maps. The power spectra are perfectly consistent with the lens lambda CDM expectation here, the red line, except for 5.2 sigma excess in the B mode spectrum at the low multipoles here. So we've performed extensive studies over the 4 years that we've been analyzing this data set that strongly argue against the systematics origin for this excess signal. What we can say about foregrounds is that they do not appear to be a large fraction of the signal according to the evidence that we could bring to bear from within our data set. So that involves the foreground projections from those pre-Planck models, the lack of apparent cross-correlations, they're low, the CMB-like spectral index, and the B-mode spectrum or distribution that seems to be traced out here. Each of those lines of evidence are relatively weak on their own. I think it's important to recognize. Okay. So taken together, I think the data on the face of it favor a tensor over a dust explanation, but it's far from conclusive. So the implied value of R is 0.2 with this error bar, and that value will shift down depending on what the actual foreground level winds up being. So what I'll say about the developments since March, this is my last slide, is that we announced this result, and there's been intense media and science community interest. I'll say it caught us by surprise just how intense the interest was, both from the media and the science community, particularly the media. So there have been many early instrumental questions. So lots of probing at our result and the ways in which systematics might have entered into it. And my own impression is that most of these seem to have faded now, and that the key concerns that have been identified seem to have boiled down to the fact that the original spectral index constraint that we reported was only for the entire signal, didn't include the lensing signal. And this is true, so that's now, we offer both constraints in the current version of our paper. And it's a relatively small effect, I would say, because in both cases, you know, it's of order 2 sigma. It's not convincing statistics either way, but it's also not zero evidence. It's something that you can't take to the bank, but I think that you have to regard as the direction the data are currently pointing. So the other piece of evidence that has come out that I think is a key one is that new papers have appeared from Planck in May, 4 new papers on dust polarization properties. So these papers so far have specifically masked out low foreground regions like our own due to the fact that they're not dominated by dust, and the systematics uncertainties in those regions are not small. But the data that they do show us shows a trend to higher polarization in the lowest dust regions. So 4% is a typical polarization fraction for dust across the sky, as the pre-Planck models suggested. But the data are also showing us that greater than 10% polarization fraction is apparent in some regions. About 10% of the sky has polarization that high. So the PRL final version of our paper that appeared last week had very little modification to our analysis, some clarification of the wording, but most important, we've clarified the fact that the uncertainty on the interpretation has increased in light of the new information that's come out. And so this key science question, does this data set show us evidence for tensors, or really is it all just dust, is one that I think we have to regard as open right now. And getting more data is now more important than ever. And so I'll just say what's happening on that front is that right now the Keck array in 2014 is running with 2 receivers at 100 gigahertz, and already the sensitivity of BICEP2 at that frequency has been surpassed. So the data we have in the can is significantly more powerful than the data that we've shown for constraining the spectral index of this signal, and that should help us discriminate its origin. We'll soon tighten the spectral index constraint, and we're hoping to have that done as quickly as we can. And meanwhile, lots of other experiments are also working on this. So I should mention them all. I'll run through it very fast. SPT pole on the same patch of sky, so we'll be doing a cross spectrum with them. But also polar bear, Princeton experiments here, ACT pole, ABS, the spider balloon, which we hope will fly this coming year, EBEX, which has already flown and has a polarization data set. And of course, Planck will have a new paper out soon on polarized dust power that we hope will include our region as well. And perhaps most exciting is in the last few weeks, The Planck team and the BICEP2 team have been talking directly about plans for doing joint map analysis and beginning this as quickly as we can. I think both sides are now very enthusiastic and see this as really the key path forward to answering the science questions at hand. What fraction of the B-mode detection that we've reported is dust, and is there firm evidence for a primordial component to it? The most powerful way to advance the science is definitely going to be collecting more data and bringing it all to bear together in a joint analysis. So thank you very much.